Hi, and welcome to the Module 1, Section 10 lesson. We're going to talk about equivalent rates in this video. Let's look at the definition here. Two rates are called equivalent. They're also known as indifference rates, and I'll come back to that at the end of the video. But they're called equivalent over a given time period. You have to be given a certain time period. If they yield the same periodic accumulation factor over that period. Now, if they yield the same periodic accumulation factor over the period, then the periodic discount factor over that period is just the reciprocal of the periodic accumulation factor over that period. So if you have two rates that are given the same periodic accumulation factors, when you take reciprocals of both of them, they're giving you the same periodic discount factor over that period. And so you could use either periodic accumulation factors or periodic discount factors in your equations to solve in order to get equivalent rates. So again, you have these two rates. You want to look at what the periodic, well, let's look at an example. So let's say that we're given, on the one hand, the rate that we're given is given to us as a force of interest. It's a delta t equal 0.1 divided by 1 plus 0.1 t. And then the question is, well, determine the equivalent nominal rate of discount compounded monthly over the period extending from time 2.25 to 2.75. And so in the solution, again, on the one hand, I have this delta t. On the other hand, I'm seeking its equivalent d upper 12 over the period extending from time 2.25 to 2.75. Now, if in this case we're seeking a value of a d upper 12, d is a discount rate. It's a nominal rate, but it's a discount rate. Generally, it's more efficient if you're seeking a discount rate to use discount factors. If you're seeking an interest rate, then use accumulation factors. I'm seeking a discount rate, d upper 12 here. So I'm going to look at the periodic discount factor over this period then. And the periodic discount factor over the period from 2.75 back to time 2.25 is this ratio of accumulation functions. So I need to know what the accumulation functions are in the different situations. Okay, so now let's start with the force of interest. I see this force of interest. At this point in the game here, you ought to be able to look at that force of interest and say that's the force of interest for a simple interest accumulation with an I value of 0.1. I just by observation recognize that. And simple interest accumulation, I get A of t equal 1 plus 0.1 t. So you should get to the accumulation function from that particular force of interest in a matter of seconds. However, there's another way to show this, so let me show you a second way to get to the same result. I look at I've got the force of interest, and I'm trying to recover the accumulation function. I see the force of interest as a fraction, so I automatically think to myself, does it fit this special class of accumulation functions? Does it fit the special class of forces of interest where they're of the form some constant times a fraction, where the numerator is the derivative of the denominator? And I look at it, and it fits it exactly. So if I take the denominator to be f of t equal 1 plus 0.1 t, then the numerator is 0.1, and I could use a c value of a 1, and I don't have to tweak the force of interest at all to put it in this form. So it's this special case of the force of interest, and from a previous video then I know that the accumulation function will be of this form. Plug in the f of t, notice f of 0 is a 1, c is 1, so I just get that the accumulation function is 1 plus 0.1 t, which I already knew from before by just recognizing it. So it's a lot quicker if you just recognize that when you see a force of interest of that form, then that is corresponding to a simple interest accumulation. Okay, once I got the accumulation function, I can calculate what the periodic discount factor is from time 2.75 back to time 2.25. I just plug in those values for t, and I'm going to take out the middle expression there and just write that I recognize then that the periodic discount factor over this period is a 1.225 divided by 1.275. Now, I'd like to make an observation here, and that is I'm given a delta t, and I'm talking about t values. Well, anytime you're given a delta t, the time is measured in years, so t is measured in years. So I'm looking at going from a time value or from year the time value 2.25 to 2.75, that's half a year. In other words, this periodic discount factor that I just calculated is a semi-annual discount factor for the specific semi-annual period from time 2.75 back to time 2.25. So it is a semi-annual discount factor for that specific time period. So now, I look at, well, what if I was using a D upper 12? Can I calculate what a semi-annual discount factor would be using a D upper 12? And then I would set it equal to that semi-annual discount factor. And then solve, and those would give me equivalent rates. So that's the direction that we're going at this point. Now, you ought to be a pro at this. When you see a D upper 12, what are you going to do? You divide it by 12, and that gives you in this case, that would be the monthly effective discount rate. Subtract that from 1, that gives you the monthly discount factor. And so the semi-annual discount factor would be the monthly discount factor to the 6th power. And so I skipped a few steps here, but you ought to be a pro at this by now. So hopefully you agree with this. Look back at some previous videos if you don't get that. Now, the point here is that I kind of slipped a word in here, and I said, I was kind of sneaky. I said, that's the semi-annual discount factor. It is. It's the semi-annual discount factor for every semi-annual period. Every semi-annual period has the same semi-annual discount factor when we're compounding, and it would be this if we're compounding using a nominal discount rate compounded monthly. Okay, it's true for every semi-annual discount factor, every semi-annual period. That's the semi-annual discount factor. So in particular, that's the semi-annual discount factor for the period from 2.75 back to 2.25. So I would set that expression equal to the 1.225 divided by 1.275, and now I've set these periodic discount factors equal to each other for the given period, and I solve for the D upper 12, and I get a 7.97% interest rate as the equivalent rate. Now, a little while ago I said it's also known as an indifference rate. So what do I mean by that? Well, so let me explain that. Let's say that you've got some money that you want to invest, and you've got a couple of banks that you're working with, and one bank is telling you, let me simplify this for just a second. The delta T, instead of telling you that one bank is giving you a crediting interest using that delta T, I'm recognizing that delta T is the same as the delta T for a 10% simple interest accumulation. So let's say that you have one bank that says, oh, I'm going to give you a 10% simple interest rate over the time period from time 2.25 to time 2.75. And another bank says, oh, I'm going to give you a 7.97% nominal rate of discount compounded monthly over that same time period. Where are you going to put your money? Well, because they're equivalent rates, you should be indifferent to where you're going to put your money, which bank you're going to put your money in, because they're going to give you, it's going to result in the same amount. Whatever you put in at time 2.25 is going to result in the same amount at time 2.75, whether you put it in to the one bank offering you a 10% simple interest rate over that period, or the other bank that's offering you a 7.97% discount rate compounded monthly over that period. That's why you should be indifferent to it. And it's a way of comparing. It's very practical. It's a way of comparing two different rates and which one's going to be better for you. You know, if one bank was offering you 8%, the D upper 12 as an 8%, you were deciding where to invest your money, you'd say, oh, well, I'm going to invest my money in the bank that's offering me the higher rate, the D upper 12 of 8%. On the other hand, if you were borrowing money and you were paying interest, then one bank that's offering you a 10% interest rate over the simple interest rate over that time period, and the other bank says we're going to charge you an 8% discount rate compounded monthly over that period. Well, of course, then you should go with the bank that's offering you the 10% simple interest rate. So it's a way of comparing rates and very practical stuff here. Okay, so I will see you in the next video.